Hello, thanks for joining me. It's Ollie Epsom again, and today we are going to look at wind power. So wind farms, specifically offshore wind farms. This is part one of a multi-part presentation that I anticipate to be 3 presentations. So without any further ado, let's just jump straight into it. What are we going to look at today? So in today's presentation, we are going to cover why do we need renewable energy? So why are we doing this in the first place? Obviously, there will be the odd cynical aside down there as to the fact that we're obviously doing it because we want money, but nonetheless, we do not live in the sort of Jeff Bezos, Elon Musk world of a libertarian, free state. We obviously live in a world where there's quite a lot of manipulation of the market, and therefore the market has effectively been created to make renewable energy attractive. Why is that? What forms of renewable energy exist? I'm going to go over why, of all the different forms of renewable energy, wind in particular in Northern Europe is a good form of energy to use. Now, I must have a little caveat on this presentation that the vast majority of my experience in offshore wind has been in the UK in general, and you could also extend that experience in terms of the attributes of that to Northern Europe. Different parts of the world do have different requirements. I'm going to touch on them in some points of this presentation, but if you look at what I'm saying and go, oh, that doesn't make any sense to me because I live in Taiwan or something, I do have to apologize in advance that this is predominantly a Northern European biased presentation, because firstly, that's where my experience is, and secondly, Northern Europe really is the hub of offshore wind in the world at the moment. Why is wind a popular choice? So what makes wind better than other forms of renewable energy for certain applications? And we'll look at the general layout of an offshore wind farm. Now, if I was a professional, I would correct that typo before continuing, but obviously I am not, so we're going to have to live with it. In part 2 of the presentation, we're going to look at much more details about the design and manufacture of wind turbines. So I know what you guys want. Obviously, you want me to talk for hours in detail about the precise definition of a back-to-back inverter. And yes, we can talk about geared and gearless turbines, and we can talk about yaw drive mechanisms, and we can talk about permanent magnet generators and all that kind of thing. Yes, we will do that, but we'll predominantly do that in part 2. Part 1 is more just a general introduction to the concept. In part 3, I'm going to look at a bit more detail about how the wind farm is laid out. So not just, oh, it is laid out and you have these things, but what goes into making that layout in the first place, how we start it, and of course the construction and operation of the wind farm, which, don't forget, is one of the things that makes offshore wind farms more expensive than onshore wind farms, because we have to build these things at sea. So I'm going to go through that with you and explain how that is done. Let's get going. The first question that I asked is, why do we need renewable energy in the first place? Now, this is not a presentation on global warming or global climate change, and it is not a presentation on the dangers of pollution caused by humanity, and it's not a presentation on the fact that we are living in the 5th mass extinction event and we are responsible for it. All of those are very interesting topics which I have a lot of interest in, but that's not what this presentation is about. If you're interested in those things, there are plenty of very good presentations on them on YouTube, and I can recommend Potholer 54 as one very good starting source. But there are 2 main reasons why we need, not want, renewable energy, and those are climate change and pollution. Now, I'm going to make a couple of statements here, and if you want to know more, there are thousands and thousands of journals online available to you at no cost, which can help. However, I've put 2 links down here on the bottom right to sort of more accessible entry-level stuff that really should convince even the most skeptical people. And if you want to know more, they will tell you and provide links as to where you can get it from. So to be clear, the scientific research, not some trawler man off Shetland dumping a thermometer in the sea and telling me that the temperature's gone down for the last 40 years he's been doing it. The scientific research on anthropogenic global climate change overwhelmingly concludes that it's real. All right. Now, we live in a time, I would suggest, where most people in the media have forgotten what it is to be a reporter. So obsessed with balance, if one scientist comes on the show and says global climate change is happening, the media feels that in order to provide balance, it must get somebody else to say it isn't. In other words, if one person tells them it's raining and another person tells them it isn't, they will print both stories instead of looking out of the fucking window and checking. So we have been somewhat conditioned to consider that there is a genuine scientific debate on global climate change. And the reality is that there really isn't. Over 97% of climate scientists agree that anthropogenic global climate change is existing. Now, there are ongoing discussions as to the severity of it and the timelines of it. So by that I mean, is it going to be really bad really quickly, or is it going to be really, really bad really quickly? But what there is not any serious debate about is whether or not climate change is happening, whether or not we're responsible, and whether or not it's a bad thing. And on this chart on the right hand side of the graph, you can see a very simplistic summary of climate change since 1880 up to 2020 from various temperature sources. Now, what it's important to realize here is that these are not just point sources. You know, we've not measured the temperature in Covent Garden every day since 1880 and put it on a chart. We obviously have done that, but that's not what this chart represents. This is global average temperatures. As you can see pretty clearly, they're going up, and they're going up very, very quickly. And wouldn't you know, that rise in temperature corresponds very neatly to the rise in carbon dioxide, which we've also measured, which has been generated by people. So about this, there really is no debate, and that is not something that I'm going to spend a lot of time in this presentation talking about. If you want me to do a presentation on climate change, let me know in the comments. Furthermore, to a very large extent, the damage has already been done. It's going to be very difficult to lower the temperature of the planet anytime soon. But the more we continue to burn fossil fuels and the more we continue to increase the emissions of CO2, then the severity of global climate change is going to get worse, and the speed at which it happens is going to get worse. So it's not even a case of saying, oh, if we reduce our emissions to a certain amount, we'll be fine. We won't be fine. If we continue to burn fossil fuels, we will continue to experience increasing severity and increasingly fast climate change. So we need to do something about that. Secondly, and this is a much more immediate concern for many people, and I was quite surprised actually at when I looked into the numbers on this, that in addition, the environmental pollution caused by fossil fuel production and consumption causes millions, and yes, I mean millions there. I was surprised by that. I assumed it would be thousands or maybe hundreds of thousands, but it causes millions of premature deaths annually. In fact, some studies show that in China alone, there's over 2 million Chinese people die every single year earlier than they should do as a result of environmental pollution. Now, I know obviously my audience are not fools, so you have to quantify this as to what does that actually mean, premature death. I mean, obviously we get killed from many things. all the time. So, you know, how do you measure that? And again, I accept that that is a in-depth subject, and putting a bombastic statement about millions of deaths through pollution is kind of inviting accusations of clickbait. What I'd like you to do is just trust me on this. And again, it's not something that I want to spend a lot of time discussing on this presentation, but it is something that's an important background to it. So, in summary, the main two reasons why we need renewable energy are climate change and pollution. We need to stop burning fossil fuels. Renewable energy is the most viable way of doing that for the majority of the world. And before you all start screaming nuclear at me, I will come on to that. Having just spent some minutes discussing pollution and climate change as a reason why we need renewable energy, many of you may have been wondering why I didn't mention another very important reason. But fear not, here it is. So the exhaustion of fossil and, to a lesser extent, but a real extent that I shall touch on very briefly, nuclear fuels. Even if climate change is not real, and it is real, and even if we lived in an amazing world where we could burn as much fossil fuels as we liked and not hurt anyone and not kill anyone and not destroy our environment, the reality is that fossil fuels are a non-renewable fixed resource. Eventually, at some point, we will run out of them. They are non-renewable. Even without consumption, even if we stopped burning fossil fuels tomorrow and we turned into some science fiction civilization that could live for millions or even billions of years, the fossil fuels would not reform, or at least they would be very unlikely to reform. And the reason being that the fossil fuels that we have, that we're currently burning, we often refer to them erroneously as dinosaur fuel. Well, actually it's not. The majority of the fossil fuels, there are some exceptions, for example natural gas, the majority of fossil fuels were created during the late Carboniferous and Permian times. And the reason for that is that at the time the entire Earth was hot, it was humid, and it was covered in, for want of a better word, forests, although there were no real trees then, they were more like giant ferns. Now, as these forests died, or natural turnover of the forest, the ferns died, instead of rotting away as they do now, they simply got buried underneath all the new ferns that were coming up, essentially locking vast quantities of carbon in the ground, which eventually fossilized into coal and oil and to some extent natural gas. Now, the reason that that happened is because at the time there were no bacteria to rot the dead matter, the dead vegetation, as there is now. So the Carboniferous and Permian times were pre-Triassic. So the Permian time was ended about 250 million years ago off the top of my head. So that was during the Great Dying, the Permian Triassic extinction event. And the Triassic was the first of the three ages that led to the dinosaurs, although dinosaurs themselves, you could argue, only really came out in the late Triassic. So they're not really dinosaur fuels, they were made a lot earlier than that. And even, as I say, if we stopped using them, and even if we left the planet for millions of years, it's unlikely that any more fossil fuels would be created here. Once it's gone, it's gone. There is obviously a continuous argument as to what type of fossil fuels we will run out of and when we will run out of them. These estimates range from 50 years for oil to 400 years for natural gas, depending on future discoveries, depending on the technologies we develop to dig it out of the ground, depending on our consumption rates, depending on legislation and so on and so forth. people in the audience may be saying, oh, I heard in the 1960s that we'd be out of oil by, you know, the year 2000 and so on. And that is a real phenomenon. There is a lot of this stuff in the ground. And as technology develops, it's true that we can extract more and more of it. But we're also, as you can see on this graph on the right, we are also using much more of it. So not only do we need to find more of it and dig more of it out of the ground in order to supply our ever increasing appetite for fossil fuels, but that is simply going to increase the rate at which we exhaust a fixed, finite resource. Now, incidentally, this is a more serious event than the exhaustion of other natural resources. So all natural resources will eventually be used. So, for example, we often talk about peak oil, meaning the point at which we pull the most oil out of the ground, after which the price will go up and the demand will go down and so forth. But that'll happen in principle for everything. You know, it will be peak iron, peak copper, peak vanadium, whatever. That will happen. However, we can recycle and reuse these elements, whereas we cannot recycle and reuse oil, and we can't reuse and recycle gas, and we can't reuse and recycle coal. So it's a lot less, you know, the periods in which peak iron and peak copper are going to occur are realistically millennia away. In addition, we know that these elements are relatively common in the universe, and for example, asteroids are full of them, and in a few thousand years we may be able to get it out of them. What we won't be able to do is get oil out of an asteroid. So realistically, whether you say it's tomorrow, whether you say it's 50 years, whether you say it's 400 years, we're going to run out of this stuff. So let's cut the crap and stop burning it. Again, nuclear. I know you're going to mention nuclear, and I'm going to be a bit of an asshole here, and I'm going to point out that nuclear fission uses uranium-235. Now, just as I said that fossil fuels will not ever be rebuilt on the Earth, or it's very unlikely, I can say with absolute certainty that U-235 won't be. U-235 was created in a supernova or a neutron star collision. There is some disagreement on that. Billions of years ago, and those elements coalesced and made the sun, and they made the Earth. What U-235 we have is what U-235 we have. We're not going to get any more unless we find a way of mining a supernova nearby. So it's also a non-renewable resource. At the current rate, and I emphasize current rate of consumption, U-235 in the Earth's crust is estimated to last about 80 years. Now, our consumption of U-235 is not particularly high at the moment. So if we were to massively expand our nuclear systems, then we would naturally start to run out of U-235 much quicker. Well, that's pretty alarming, 80 years. It's also extremely simplistic, as most of my viewers will be aware. Don't think that I'm not aware. The way we use U-235 at the moment is incredibly inefficient. There's no doubt about that. When the fuel that is in reactors is exhausted and can no longer be burned, we've actually only burned a very small fraction of the U-235 that was in there. But the fuel has been poisoned to such an extent that we can't burn it efficiently anymore. If you want to know more about that, I recommend you watch my nuclear submarine propulsion series. In principle, we can take that spent fuel, we can burn it in heavy water reactors, we can reprocess it, which extracts the unburnt U-235 from the fuel and reuses it. And of course, we can use fast breeder reactors. Now, these are all entirely plausible technologies. In many cases, they have been tried. In the UK in particular, we've had fast breeder reactors tested since the 1960s. We also have nuclear reprocessing plants, but due predominantly, it have to be said, to political reasons, they have not been developed to a high standard of operation. Now, there's no technical reason why that could not be done, but the fact remains that it is not done. It has not been done. And therefore, at the present rate of consumption, we will run out of U235. There are further caveats to this along the lines of the spent fuel that we have has not been permanently buried or disposed of, so there's nothing to stop us in principle in future reprocessing the spent fuel that we already have, which is in temporary storage, and so on and so on. So I don't want to be too alarmist with this 80-year argument. Realistically, that is not the case. Even if it was, the majority of U235 that we know of is not necessarily in the Earth's crust. An awful lot of it is in the oceans, and in principle there's enough in the oceans at the current rate of consumption to last us for millennia, but obviously we would have to extract it. So it is clear that we need a form of energy that does not rely on digging stuff out of the ground and combining it with oxygen. And to a lesser extent, it would be very nice if we could have a form of energy that does not require digging uranium out of the ground and fissioning it. In an ideal world, yeah, we would probably have nuclear fusion, but we're not in an ideal world, and we don't, and we have to do something today. More accurately, we had to do something about 50 years ago, but, and it's an expression I hate, we are where we are. So we decided we need renewable energy. Let's look at the different types of renewable energy available to us. Let's not spend too much time debating the time renewable energy. I think it's pretty clear what I mean by it at this point. I mean some means of getting electricity, or in other circumstances direct heat, but we're primarily focused on electricity here, that does not require me to dig stuff out of the ground and shovel it into a furnace or a nuclear reactor. Ultimately, the vast majority of renewable energy systems come from the sun. There are two main exceptions, only one of which I'm going to talk about here, but the majority of them come from the sun ultimately. So really we're looking at energy conversion systems from nuclear fusion. Now, first type I'm going to mention is tidal. Tidal energy is one of the two exceptions, the other being geothermal, which I haven't actually mentioned here, of renewable energy that predominantly do not come from the sun. So tidal energy comes from the movement of tides, and the tides, as any schoolchild will tell you, come from the moon. Except, of course, they don't. They actually come from a combination of the moon and the sun in about a 60-40 split. So the majority of it comes from the moon, but a significant portion of it comes from the sun. Even if we took the moon away, we would still experience tides on Earth, as would any planet. Although the sun is obviously orders of magnitude bigger than the moon, it's also orders of magnitude further away, and that's why the contribution of the sun is actually less than the contribution of the moon. Now, the practical effects of the tides on Earth is that it makes water in the oceans move about. We can exploit that movement, and from it we can draw electricity. There's two main ways of doing this. There's the tidal barrage method, where you effectively dam an estuary and you put almost conventional hydropower turbines in it. That has been done in France many years ago, and it's very successful, but there are some environmental problems with it. Since at least the early 1900s, a similar discussion has taken place as to whether to build such a scheme across the Severn estuary in London. It would probably power 10% of the UK, but it would also devastate all the wetlands which are used by wading birds and so on and so forth. So most current tidal development is using effectively underwater wind turbines. This one here I've got on a picture is from the Nova company in Scotland. A lot of this development has taken place in Scotland, and there are a few trial schemes in operation. So advantages are it's got a very high energy density. So in principle, say for a multi-megawatt tidal turbine, the swept area is very, very much smaller than a wind turbine. It's not as physically big, but of course the forces are correspondingly high. And of course it is highly predictable. So again, with the exception of geothermal and to a certain extent hydro, tidal power has the advantage of being predictable. Now, obviously, if you have a solar panel in a desert, that's also fairly predictable, but not as predictable as tidal. Furthermore, although you get 2 tides a day, or 4 if you're in the Isle of Wight, the land mass heavily influences the time and the height of the tides, so that if you lived in a country like the UK, you can get different tides at different parts of the country, and in principle, if you had enough of these machines, you could in principle get a nice smooth power delivery. However, it's very difficult to do, and it's just not a commercial technology at the moment. There's a lot of research going on to try and make it commercial, and I say a lot of research almost in air quotes, because there isn't actually a great deal of money being spent on this in real terms. There are some trial farms going on in the UK now, and they are on the verge of being commercial, but they are chasing a moving target, which is onshore and offshore wind, in terms of how to make it cheap enough. And because the technology just isn't as mature as those, and because it's more difficult, that's not happening. Why is such a relatively small amount of money being invested in tidal? Well, it's quite straightforward, really. It's most of the tidal resource in the world is actually in UK waters, and there's not many other places in the world which have got high velocity tidal streams that could make use of this technology. If you live in the Mediterranean or anywhere around the Pacific, for example, you have very little to none in terms of tidal energy. There may be a few inlets and things off China and South Korea that you could extract a couple of gigawatts from, but you know, not anything like what you can do with offshore wind. And because the UK is not particularly forward thinking when it comes to encouraging research and development, then there isn't a lot of money being spent on it, which I think is a shame. A lot of commonalities exist between tidal and hydro. So hydroelectricity is obviously the most developed renewable energy system in the world. It produces double digits probably in terms of electricity consumption. And there are many countries in the world where it produces very, very high proportions of the energy. So for example, Norway, Switzerland may well produce 50% or more of the total electricity used in those countries. Same reason, it's water moving, or water at high pressure, has got a very high energy density. Now, it is controllable and to some extent predictable, depending on where you build it and what you build it with, but a lot of these systems can and do operate year round. And even if they don't operate year round, it is generally a known fact, or with a reasonable degree of confidence, when they can operate. Another advantage that I should have put there is the longevity. There are plenty of hydro stations kicking about that are in excess of 100 years old now, and which are still using the original generation equipment and the original turbines. This one I've shown in the picture is Loch Sloy in Scotland. Again, this has decades and decades of successful use, and you can find these all over Scotland. But again, sorry to be so UK based, but most of these systems in Scotland were built between the 1920s and the 1960s, and effectively we've already done everything there is to do. There isn't a lot more, even in principle, never mind practice, that we could achieve in Scotland, because we don't have the head height. In other words, the maximum drop are sort of 400 to 600 meters, and that's really not a lot. We've exploited the vast majority of places where you can get that head. If we were Norway, for example, where you can get a couple of thousand meters, or Switzerland, where you might get even more, or countries like Brazil, which have enormous rivers and things, then hydro would be a much better resource. But actually, as far as the UK, and in general, stand fast Norway, much of Northern Europe, hydro is not really on the cards, or it's not really available. In addition, there are environmental concerns to hydro stations, which again, you can imagine you're damming a big river or you're creating an artificial lake and so on. That can be seriously problematic to the wildlife in there. Solar. Solar is a big deal. It has huge advantages. It's got no moving parts, or at least it should not have any moving parts. Occasionally it's true that solar farms will have some sort of solar tracker, but often they don't. So I'll write that. But even if they have a solar tracker, that's a very slow moving part. And they are linearly scalable. So what do I mean by linearly scalable? I mean that 1 square meter of solar panels will create a given amount of electricity from the sun. 2 square meters will create double that, 3 square meters will create quadruple that, and so on. Now, that is not the case with wind turbines or tidal turbines for a wide range of reasons. Small wind turbines are not very good. And that's not just because, for example, if you halve the diameter of a wind turbine, you obviously reduce the swept area by 4. Well, any fool could tell you that. If you halve the swept area of a wind turbine, it will not create half the power. And the reasons for that are many, but one of the main ones, and perhaps the obvious ones, is the bigger the diameter of the wind turbine, the higher up you can put it, and the steadier the wind that it can get. Again, that's not really a consideration with solar power, which is why solar power on domestic rooftops does make sense, because if you have enough of it on domestic rooftops, it will be the equivalent of a large field like this one. Except that many rooftops are unsuitable for it, but let's ignore that for a second. There are some issues with it. Obviously, it does not operate at night, and in many countries, night is quite long. And the second one, which often doesn't get a lot of press, is that it's less suitable for cool countries. Now, this is not necessarily because cool countries don't have a high enough solar incidence or irradiance to make it economically viable. But in cool countries, we don't tend to use air conditioning, meaning that in the summer, our electricity demand often goes down, not up. Now, if you were in a hotter country, the electricity demand in the summer will go up. But that is also when your solar irradiance goes up, which means your solar farm will generate more. So solar power is less suitable, I would say, for countries, Northern European countries in particular, where the electricity demand is higher in the winter than in the summer. And that tends to be why solar is more attractive in sort of equatorial regions, even though it's not necessarily the case that a solar farm, just because it's, say, north of the Tropic of Cancer, is gonna produce significantly less energy than one on the equator. Don't forget that environmental features such as air pollution and humidity dramatically affect the amount of energy that these things can create. So it may well be that a farm slightly further north, if it's got better weather conditions, will create more energy. But as I say, the main issue is the energy demand higher in the summer than winter and not operating at night. There are other issues with solar panels, for example, the materials that make them coming from fairly despicable regimes, and I am going to name names, China, but these are things that in principle could be solved. So that does bring us to wind. Wind is being wildly successful. It is a commercial energy technology, as in onshore wind farms are being built today and have been built for a number of years, where they do not require any subsidy to operate. In the UK today, onshore wind is the lowest cost form of electricity. It is a highly established commercial industry with considerable factories, industrial knowledge, operations and maintenance experience, and so on. In the UK in particular, and Northern Europe in general, there is an enormous wind resource. We are a very windy part of the world and we can make use of this energy. But wind power has a low energy density, meaning you have to build gigantic turbines. So this one in the picture has got blades which are in the region of 60 meters long, and modern blades are being built now which are 120 meters long. And that is big, you know, with 240-meter diameter wind turbines. The tip height is going to be taller than the Eiffel Tower, and that's going to be generating, what, 20 megawatts? So you need a lot of them. Wind itself is difficult to predict. It comes and goes, obviously. Again, it won't be windy all the time, and even in a relatively big country, it might not be windy somewhere all the time. So that is a concern. Furthermore, offshore wind farms are still relatively expensive, and I will talk about that later. And that later is now. So let's look at some advantages and disadvantages of offshore and onshore wind farms, because of course we do build onshore and we build offshore. So why do we do that? Obviously it's going to be more difficult and expensive to build offshore, so there's got to be a good reason for it, and there are several. So when we build an offshore wind farm, we get a much higher capacity factor. So I've quoted here, the capacity factor at Beatrice wind farm is well over 40%. Now Beatrice was one of the farms I worked on. It's an offshore wind farm off the coast of Scotland, and it has performed very well. What does that mean? Let's say, for numbers, I build a 100 megawatt farm. If it operates at a capacity factor of 40%, then on average it will generate 40 megawatts on average. Sometimes it will generate 100, sometimes it will generate 90, sometimes it will generate 10, but on average it will generate 40. Now in an ideal world, we would build a wind farm with a capacity factor of 100, but of course that's not possible because the wind comes and goes. And if we built a wind farm which was under capacity, for example, so it had a high capacity factor, it would effectively not be exploiting the wind when the wind does blow. So on onshore wind farms these days, 40% is a good target. Offshore wind farms may well be well over 50% now. So Beatrice is a couple of years old and I don't have access to the latest data. So why is that capacity factor higher offshore? Well, generally because we can build very much bigger turbines, there's much more land available, and there's no obstacles. When you build a wind farm on land, you are hamstrung by having to build it on mountains, around hills, there's fences, there's forests, there's some arsehole's house in the way. You can get very strange effects that are very difficult to predict. Even with modern CFD, it's difficult to get it right. And there are a number of wind farms that I know of in the UK with capacity factors well below 40%. So I'm talking maybe in the worst case down in the low 30s or even high 20s for a particularly bad farm. That tends not to happen offshore. Furthermore, modelling improves all the time, so the amount of calculations that we can do improves all the time, so we can get better and better wind farms with higher and higher capacity factors. Obviously, we can build much bigger farms because it's in the sea, so there's a lot more quote-unquote land available. It's much easier to get at. The bigger turbines is because we don't have to drive these turbines along an access road, as you can see here in this clip at the back from the Stromlerg wind farm, which I also worked in. You can build turbines with blades double the length of what you see in this clip easily. The only limit is the factory, because the factory is typically by the sea and they go straight from the factory and onto the boat. And there are less NIMBYs, so there's less NIMBYs not in my backyard. You know NIMBYs, right? They're the people who go, oh, you know, I just think it's a load of rubbish that we have these wind farms, and they really don't generate any electricity, and they spoil my view, and I'm an arsehole. That sort of people. They tend not to care as much when you build it offshore, which means they don't object as much. With NIMBYs, obviously, they respond very well to money. So if you keep giving them money, they will tend to shut up. But there's always one or two who are in it to make a point, and they're the ones you have to worry about. So obviously there's disadvantages as well. Once you start building something in the sea, it's difficult to access. Why? Because it's in the sea. And anyone who's spent any time at, around or on the sea will know that the sea is not friendly. The sea does not care what you think. It's therefore the case that a very small failure on a turbine, a cooling fan that maybe costs £20, that fails in a computer box. That computer shuts down, the whole wind turbine producing 7 to 12 megawatts, depending on what size it is, shuts down. It happens in December and you can't get to it until maybe March because of the weather. Now you've lost a considerable amount of electricity from that one component. So it is difficult to access and difficult to maintain. Obviously not all sea floors are suitable. The sea in general is deep, and these things, with one or two exceptions, are all bottom mounted on foundations. I'll go into that in part 2. Anything much above 60 meters becomes difficult, and 60 meters is not very deep when you think about the majority of the ocean being thousands of meters deep. So realistically we build these things on sandbanks. That does have an advantage to some extent in the when we build these things in shallower water, they tend not to be as many ships around to smash into them, but it does limit our options. We create a lot of interference with marine life when we're constructing it. These things are very noisy to build, particularly piling operations for foundations. And again, I will get into that more in part 3, but for marine mammals in particular that rely on sonar for navigating and operating under the sea, some arsehole coming along with a impact hammer and smacking some piles into the seafloor is literally a death sentence, and this noise travels hundreds and hundreds of nautical miles through the sea and deafens the poor creatures. So it's very difficult, and that is a disadvantage. And finally, it is expensive, although that is a relative term. It's 50% more expensive than onshore wind as a rule of thumb. That said, we're still looking at prices of around 50 to 60 euros per megawatt hour. Which, in principle, at your door would mean 5 to 6 cents per kilowatt hour. But of course, by the time it gets to you, it doesn't cost anything like that. So it is relatively cheap, but it's relatively more than onshore wind. Here, for example, we can see a breakdown of the percentage costs of a real offshore wind farm, and I'm not going to say which one. I have doctored it slightly to avoid that. In general, we can say the WTG, which stands for wind turbine supply, that's about 40% of the total costs. And the wind turbine foundation supply is about another 30%. So by far the most expensive part of an offshore wind farm is the bit that you can see. It's basically the turbine and the foundation on which it sits. The other things we've got are array cables. So we've got export and inter-array cables, which I'll cover later. The actual installation itself, which can be very, very expensive, offshore substations and so on. And this supply contract generally includes installation, which is why it looks bigger than it is and why installation isn't separate there. But that will be a commercial decision that's based on the farm. But those installation costs are obviously going to be very much higher than they would be if you simply get Jack Jones or whoever to drive his lorry up a hill and dump some wind turbines on a hard standing where some local guy with a crane can pick them up and shove them in the ground for you. It's much more complicated offshore, and that's why it's more expensive. But generally speaking, the fact that you can build it because there's no objections and there's no NIMBYs, and the fact that it is economic enough to make a return on your investment means that we build them. And of course, the physical size of these things means that we can generate much more power anyway. Okay, so much for that. We're going to spend the next 3 slides looking at the general arrangement of a offshore wind farm. Now, bearing in mind, these things are going to be largely the same for an onshore wind farm, except instead of being mounted on the seafloor, they'll be mounted on a bog in Scotland or wherever it is that you have it. So these general major systems are going to be the same for any wind farm, but I'm focusing mainly on offshore wind farms because they're the coolest type, right? So the major systems that you have on any wind farm are the wind turbine generator foundations. So that is the bit on this diagram here that joins the turbine to the seafloor. And in a couple of slides, I've got a picture of the 2 main types of them, and I will go into them in much more detail in part 2. So the foundations that you stick the wind turbine on, as you saw, are around 30% or 20 to 30% of the cost. 30% of the cost. On top of the foundation, you shove the WTG, the wind turbine generator. That's the cool, sexy bit with the blades on it that turns and makes the electricity. But then you've got to connect the wind turbine generator to something. So you get these inter-array cables, and that is a cable that goes along between a group of turbines, and that group of turbines is called a string. So you might have anywhere from 2 to 10 turbines on a string, and this cable gets thicker as you get closer to the substation because it's carrying more power from more turbines. So on the last turbine on the string, this cable may be quite thin, or it may be made out of aluminium because it's cheaper and be the same size. So that inter-array cable takes the power from the wind turbines to your offshore substation. Now, not all wind farms have an offshore substation. If the wind farm is quite close to the shore, then these strings, these inter-array strings, will go directly onshore to the onshore substation. And a number of the early offshore wind farms do that. And Formosa 2, which is a wind farm that I'm currently, for my sins, involved with in Taiwan, also does that. But generally speaking, for a seriously sized, proper offshore wind farm, there'll be an offshore substation. So those inter-array cables will be anywhere from 33 to 66 kV. And then the onshore substation will typically transform that up to, say, 220 kV for transfer down the export cable, which goes from the onshore substation all the way along shore into the onshore substation. And from the onshore substation, then it just gets connected into the normal grid. So that is the general synopsis of any wind farm anywhere in the world. There are some differences, which again I'll go into more in part 2. For example, increasingly the export cable is actually a high voltage DC system. So there are converters in the offshore substation to handle that, and converters in the onshore substation. There are advantages and disadvantages to that. You know, different array voltages, different string orientations, different switchgear, and so on. You will also, even though it's not shown here, somewhere you'll have a big port and a harbour facility and maybe a helicopter deck and an office, and that is your operation and maintenance facility where you control the wind farm from. Now, in principle, you can control the wind farm from anywhere because it's just a computer system, but you still need boats to go out and service it and fix it and do things. So typically, the operations and the maintenance facility is the same place, and typically you have actual people in an actual control room controlling the actual wind farm, and you can look out of the window and you can approximately see the farm. But that does depend. For some wind farms you might have several controlled from a central area, and you might have one O&M port that does everything, but in general there will be something there. If I give you an actual example of an offshore wind farm that I have worked on and had a lot of input in, let's look at the Beatrice offshore wind farm. I keep harping on about it, not because it's the most recent wind farm that I've worked on, but because it's built and it's operational and there's information in the public domain. So I'm not breaking any agreements by showing you information about it. The Beatrice wind farm is the first offshore wind farm in Scotland, and if I highlight Scotland here, you can see that it's actually in the Moray Firth, which is at the top right hand corner of Scotland. Here on the main graph here you can see Wick, which is one of the furthest north towns in Scotland, and down here at the bottom you have a town called Buckie, which is a seafaring town. Off the chart here and the inside we have Inverness. Now it's worth pointing out here the scale on this map. So this is in nautical miles and this is in kilometers. The area highlighted in red, which I'm now going to fill in with blue because that's the kind of guy I am, is the actual wind farm area itself. Now that, as you can see from the chart, is big, you know, and from memory it's around 10 nautical miles from the bottom to the top. So it's a considerable size. You know, there's a lot of islands, for example, in the UK, which are smaller than that. There's a lot of cities that are smaller than that. You know, 10 nautical miles is big. That would do a lot of damage to London if you dumped it over the top. And these two black lines here are the export cables. Now, Beatrice is a little bit odd in that the O&M port is in Wick, but the actual substation is in a different place down in Bucky, but that's just because of grid arrangements. So to sort this thing out, we sail out of Wick and it takes a couple of hours on our crew transfer vessels to get to the wind farm. There are also helicopter facilities. Now, if we look at the actual wind farm itself and enlarge the part that was a wind farm, you can see that I've put every wind turbine is one of these little circles. So, and some of them I've put red highlights around. That was for another purpose, but you can see incidentally from those red highlights that the turbines are arranged in straight lines, which you can do offshore because you don't have to worry about topology getting in the way. On an onshore wind farm, the turbines are almost randomly placed if you look at it from above, because they're placed in the position where they have the most aerodynamic efficiency. Now, you will also note, if I change to the pen rather than the pointer, that Beatrice has got two offshore substations. It's essentially two half wind farms, and there is a connector between the substations, and then it has two export cables, so either export cable can be linked to either substation. But although the turbines themselves are arranged in straight lines, as you can see from the ones that I've highlighted, the strings, which are the cables that connect the turbines together, are not in straight lines. They are more like a spider's web, and they go like that. So there are reasons for that, and I will go over the reasons in more detail in part 2. But for now, you need to understand that what you see when you look at a wind farm above has nothing to do with how it's electrically connected. You know, electrically, it may be very different. So Beatrice has a total capacity of 588 megawatts from its 84 turbines. At the time it went into service, it was the 4th most powerful farm in the world, but now it's just an average farm. There's around a kilometre between each turbine, although it does vary slightly, and obviously, you know, they're not in square patterns, they're in diamond patterns, so, you know, but around a kilometre. And it has two groups of 7 strings, and each string is 33 kilovolts. So the 7 strings come from each of the 2 substations, offshore substations. So each offshore substation has 7 strings, and each string has 6 turbines. And each turbine is 7 megawatts. So if you go 6 by 7 by 7, you get 588 megawatts. And remember when I said that this farm is operating at least 40% capacity factor. So that's pretty good. 2 offshore substations, 2 export cables at 220 kilovolts. Now, that is a real example of a real wind farm. And the reason I show that is to explain that what you see when you look at a wind farm from above is not necessarily related to its electrical configuration, and I will talk about that in more detail in part 2. Finally, and this is a little bit more detail than I would typically go into in part 1, which is just an introduction, I'm going to talk very briefly about foundation types. Now, the reason that I'm doing this is because when you, as a casual observer, look at a wind farm, the most obvious differentiator that you're going to see between the different types of wind farm is the foundation. There are 2 predominantly used types of foundation. They are the jacket foundation and the monopile foundation. Now, the vast majority of wind farms use the monopile foundation. Reason being, it is much cheaper. And traditionally, monopile foundations would be used anywhere from sort of 10 meters to maybe 25 meters of water depth. And if you wanted to go deeper than that, you'd have to use a jacket. So a jacket would go 25 to 55, 60 meters of water depth. But there are now big monopiles, so they call them XL monopiles. And they will go at least as good as sort of 40, 45 meters. So really we want to avoid jackets because jackets are expensive. So jackets, you've probably seen them. They're similar to what you would have seen in offshore oil. They are a sort of lattice structure that has extensive cross bracing, and they can take much higher side loads. And then you install the jacket, as you can see these jackets in the background. This is again is Beatrice wind farm under construction. These jackets in the background have already been installed, so the part of the jacket that you see above the water is only a very small part of the total jacket. The majority of it is underwater, and it may be much further underwater than this jacket, because of course you need different jackets for every depth of water on the field, and the water depth across the field varies a lot. So the monopile, on the other hand, is a much more simple, much cheaper foundation system, where there's a single pile that is embedded into the ground. So it's just one round steel tube, as opposed to multiple bits of steel tube which are formed and welded and cut together. And then this part which you see above the water, which is actually not the monopile, it's the transition piece, I will explain that in part 2, is dropped on top of the pile and then grouted, which another word would be concreted effectively into place. I'll explain that in part 2. The reason I mention it in part 1 is merely because if you ever see an offshore wind farm, the key difference that you're going to see above the water is whether it's got this jacket type foundation or whether it's got this monopile foundation. Almost all wind farms go for monopiles because they're cheaper. The only reason you use jackets is when you absolutely have to. And Beatrice was one example of that. And Formosa 3, which I'm working on at the moment, is another example of that because of the water depth. So let us call it a day and summarize part 1. What have we learned in part 1? So the main point, I think I laboured, is that renewable energy is necessary and we can't do without it. We need it. For the UK in particular, and I should say Northern Europe in general, wind is a good fit, especially offshore wind, because we've got a lot of nearshore environments, we've got a lot of sandbanks, we've got a very, very blowy country where it blows all the time. Some might say it also sucks, but that's a whole other debate. And we can generate a lot of energy from it, whereas we don't have a lot of hydro when we don't have a lot of solar. The wind farm themselves, they consist of much more than just a turbine. So the turbine, as I said, is around 35 to 40% of the total construction costs. We also have foundations, we have cables, we have substations, we have control gear, we have installation costs, we have project management costs, and then that's before we've even switched the thing on and operated and maintained it. So the big sexy bit that you see spinning around is a relatively small part of the wind farm. The most obvious visual difference between farms is the foundation type. So again, there we had jackets and monopiles. This one here, clearly monopiles, okay? And most wind farms are. I'm not sure which farm this is because I got the picture off the internet, but judging by the fancy pimped out blade tips, I'm going to guess it's Germany, because for some reason Germans love red tips on the end of their blades. Don't know why. As I said, in future presentations, we are going to look in more detail at the major components. So I'm going to talk in detail about the wind turbines. I'm going to talk in detail about the foundations, the cables, the offshore substations, and so on. And I'm also going to look at the construction and operation of the key farm components and any key challenges that we are experiencing in the industry at the moment. Thank you very much for watching. If you've got any comments or questions, please shove them in the comments and question box below. You know what to do. And I hope you enjoyed it. And if you did enjoy it, please consider liking and subscribing and watching some of my other videos. Many thanks and enjoy the rest of your day.